Hello, this is Ms. DB, and we are going to review how to do Chapter 12, Section 5 on symmetry. And we are identifying and describing symmetry in geometric figures. A little bit of vocabulary for this lesson, all to do with symmetry. And there's an example of this kind of biology application problem. So you should know that diatoms are microscopic algae that are found in aquatic water, basically. And scientists used a system that was developed in the 70s to classify these based on their symmetry. So they kind of fit in well with this lesson. A figure has symmetry if there is a transformation of the figure such that the image coincides with the pre-image. Here's an example. It has line symmetry, sometimes called reflection symmetry, if it can be reflected across a line so the image coincides with the pre-image. In other words, if you can fold it in half along a line so that one side looks exactly the same as the other side, then it has line symmetry. This line of symmetry, it divides the figure into two congruent halves. And you can see that a heart would have line symmetry because you could fold it right there and one side would look exactly the same as the other side. It's also a line of reflection if we want to go back to that kind of transformation. So what you're going to be doing for a lot of these is saying whether it has line symmetry, and if it does, draw all the lines of symmetry you can. So this one has a lot of symmetry. So if you look at this star, it's got 1, 2, 3, 4, 5, 6, 7, 8 points. And you can draw a line of symmetry through each one of those points. So that's what these are. There's one, and that line would go through 2 of the points. So there are 4 lines that go through the points. And this one. But there's also lines of symmetry that come in these concave parts of my star shape, and then there's actually 4 of those lines. So the line all the way through it, that's taking care of 2 of those. So there's 4 more lines. So 4 plus 4 is 8. So it's got 8 lines of symmetry. How about this one? It's a right triangle. It doesn't seem to have equal legs. You know, these aren't congruent lengths. If I drew a line here, no, that doesn't work. Can I draw a line maybe through here? No, that certainly doesn't work. Through here. None of these seem to be a line of symmetry because one side doesn't look exactly the same as the other. If it was an equilateral triangle, that would have line symmetry. But none of these worked, so it has no line symmetry. Not everything has line symmetry. This does, though. This has more than you might think. This has 2 if you divide it in half that way and you divide it in half that way, but there's also, you could divide it diagonally, one there and another one here. So A has line symmetry. You can divide it in half vertically or horizontally. The letter B, as written this way, would have 1 line of symmetry. You could cut it right there in half. This flag, I think it has 1 line of symmetry right through the horizontal part right there. You have to be careful with that and make sure the stars were the same on both halves. Now, next one to talk about is rotational symmetry. If you can rotate about a point by an angle greater than 0 and less than 360, because you can rotate anything 360 degrees, you would just get back to itself, so that the image coincides with the pre-image. Something can have both line symmetry and rotational symmetry, by the way, or it could have just one or the other. The angle of rotational symmetry is the smallest angle through which a figure can be rotated to coincide with itself. The number of times the figure coincides with itself as it rotates is called the order of rotational symmetry. So a square can be rotated 4 times, so it would have an order of 4. And each time you would rotate 90 degrees. So that's a, so you could, let me draw that. We could rotate 90 degrees and get the square back, and then another 90 degrees, and another 90 degrees, and another 90 degrees. And then you would get, so it has an order of 4, and the angle of rotation, or of rotational symmetry, would be 90 degrees. Rotational symmetry. I'll abbreviate a little bit. All right, so you're going to say whether or not it has, yes or no, if it has rotational symmetry. And if it's a yes, you have to say what is the angle of rotation and the order of the symmetry. So letter A, I don't think has any rotational symmetry. It does not look like you could turn that and get itself back, other than perhaps all the way around, which is not count. Oops. B, let's see, could you flip that over 180 degrees and get itself back, or would that just be reversed? So yes, you can that one. It's 180 degrees because you could flip it one time, which would be 180 degrees, and so then its order would be 2. To find the order, if you can find the angle of rotational symmetry is 180 in this one, and take 360 divided by that, you will get your order of rotation. Okay, C. It looks to me like you could rotate that 90 degrees, yep, 90 degrees, and 360 divided by 90, the order of rotation, is 4, so that's the order. You could turn that 4 times before you got back to 360, and that is your order. A is going to be a yes. You could turn that. See, there's the other, you can work it the other way too. If you can figure out the order, and then you could take 360 divided by the order, that will give you your angle of rotation if you want to work it that way. I can see that I could turn that 3 times before getting back to itself, and it would look the same each time. So that's an order of 3. B, we could turn that 1 time, 180 degrees, so that has an order of 2. And C has none, no rotational symmetry. So this one we are going to draw any lines of symmetry, and also, if it's rotational symmetry, give the angle and the order. There's no line symmetry in this one. You can, however, rotate it 180 degrees and it'll look the same, and 180 degrees always has an order of 2. This one does have lines of symmetry, so we're going to draw those in, and it also has rotational symmetry. So it's got 1, 2, 3, 4 lines of symmetry. The angle of rotation is 90 degrees, and it's got an order of 4. Now these are those little LGs that we talked about. So they're a little bit hard to see, but we are going to describe whether or not they have line symmetry, and if they do, draw them, and also rotational symmetry. So this one it's a little bit hard to see, but it does have line symmetry. This is 1, 2, 3, 4. It's got 5 of these, I guess, they look almost like little pieces of pie. So it's got 1, 2, 3, 4, 5 lines of symmetry. Remember, I don't count all the points because this is the same line as this one. So 1, 2, 3, 4, 5, because it's got 5 of these pie shapes, 3, 4, 5. And it also has rotational symmetry. The rotational symmetry would be, since it's got 5, I could turn it 5 times and it would look exactly the same. So to find the angle of rotation, you can take 360 divided by 5 is 72 degrees. And the order is 5, like we talked about. The line symmetry in B, let's count these points. 1, 2, 3, 4, 5, 6, 7. So there's going to be 7 lines of symmetry, and the order of rotation is also going to be 7. So to find the angle, we can take 360 divided by 7 to get, I guess, 51.4. I don't have that memorized, but you can do it on a calculator and find that. All right, we can find symmetry of 3-dimensional figures too. But instead of line symmetry, we talk about plane symmetry. So if you could take like a piece of paper and cut a 3-dimensional object into 2 congruent parts, then it has plane symmetry. This rectangular prism would have more than one place where you could do that. It would have what's shown, and you could also cut it parallel to the floor, to the base. It also can have symmetry about an axis. If you can picture putting a rod or a stick through that object and spinning it so that it would look the same when you spin it, then that has called symmetry about an axis. Like this cylinder has symmetry about an axis because you could spin that really infinite many of times so that it would look exactly the same. Every spot would look the same. That's symmetry about an axis. So this is looks like a rectangular or possibly a square pyramid. And is there anywhere that you could put a piece of paper and cut that so it would look exactly the same? And there is a couple places. It's kind of hard to draw, but you could cut it right there, or you could cut it right there. So it's got two plane symmetries. It also has rotational symmetry. If you pictured, sticking a chopstick through the vertex and going through the center of the base, you could spin it, and you could spin it 1, 2, 3, 4 times, and it would look exactly the same. If it's a square. If it's a rectangle, you can only spin it twice to look exactly the same. All right, how about this one? Does it have plane symmetry? I think, but I don't know about that symmetry about an axis. Let's look at their answers. There's the plane symmetry. You could cut it right in half and make 2 L's. Whoops, but it doesn't have any rotational symmetry. You could stick something through the center of this, but you would have to go all the way around 360 degrees before it would look like itself again. On these, you just have to say whether it has plane symmetry, symmetry about an axis, or no symmetry. A cone has plane symmetry. You could cut it right through the vertex in the center. I'm not very good at sketching these, but you could. That's my piece of paper. It's terrible, I know. You could also have rotational symmetry because you could put a stick, a rod through there and spin it, and it would look the same. This is a crazy looking shape. I don't think it has any symmetry. Nope. Too bizarre looking to have any symmetry there. So this is a pretty basic section. You should be able to get through it pretty quickly. If you have any questions, just let me know. Thank you.